Hi, in our last video, we talked about how solubility is governed by equilibrium. And in this video, we're going to discuss a couple of applications of solubility equilibrium. And so the first one is related to solubility and the common ion effect. We talked about the common ion effect with relation to acids and bases, but it's also really important for solubility. So it still works exactly the same way, in which you have something that you're trying to dissolve that has a cation and an anion, but then there's something else in solution that is either the cation or the anion. And so we treat this exactly the same way that we did when we were doing common ion effects in acids and bases, which is to use an ice table and add those starting concentrations to the ice table. So here's the steps you take to calculate the solubility when you have common ions present in solution. First, as always, when we're talking about solubility, we write a balanced equation for ion dissociation. Next, make the ice table and add the initial concentration of whatever your common ion is. Third, use stoichiometry to calculate concentration changes in terms of X. Fourth, calculate the equilibrium concentrations given initial concentrations and the concentration changes. Then you plug those concentrations into the KSP expression and solve for X. Then the value of X that you get is the molar solubility. You might need to convert that into plain old solubility in grams per liter if that's what the problem asks for. So let's try a problem. Here we have the KSP of calcium carbonate. So what would happen if you tried dissolving calcium carbonate, not in pure water, but in a 0.20 molar solution of sodium carbonate? So let's work through the steps. Step 1 says write a balanced equation for dissociation. So here's our balanced equation. Calcium carbonate dissociates into calcium ions and carbonate ions. There is a 1:1 ratio for that. For our ice table, we add the initial concentration of common ion. So that's what's in the solution before you put calcium carbonate in. So we have 0.20 molar of carbonate, and we have no calcium before we add our calcium carbonate. So that's going to be 0. Now we're going to calculate concentration changes in terms of X. So what changes if we put calcium carbonate into our solution? Well, in this particular case, however many moles of calcium carbonate we put in, we're going to put in the same number of moles of calcium and the same number of moles of carbonate, because it's a 1:1 ratio, right? If it was a 1:2 ratio, one of those would be 2x, but it's a 1:1 ratio, so we have plus x and plus x. So our equilibrium concentrations then are X and 0.20 plus X. Now we're going to solve for X using our KSP expression. So here's our KSP expression. It's just calcium concentration times carbonate concentration. And before we actually plug in our concentrations, let's just assume that X is going to be very small. Calcium carbonate is not very soluble. So we're going to approximate that 0.20 plus X is about the same as 0.2. So let's go ahead and plug that information into our KSP expression. We get 3.4 times 10 to the minus 9th equals X times 0.20. And it's fairly simple to solve for X here. Just divide both sides by 0.20. So we get X equals 1.7 times 10 to the minus 8th molar. This particular problem asks you to solve for molar solubility. So we're not going to do step 6, but you can imagine how we would use the molar mass of calcium carbonate to solve for that solubility if that's what the problem was asking for. Okay, so the second application of solubility equilibria is thinking about whether or not something's going to precipitate out of solution. Now, we only get precipitates if a solution is supersaturated. In other words, if there's enough cation and anion concentrations that it can no longer stay in solution. So the way that we think about supersaturation in terms of equilibrium expressions is we think about the value of our Q, the value of our reaction quotient. Remember, the reaction quotient takes the mass action expression, which is the same thing that we use to calculate our equilibrium constant, and it calculates its value at a particular point in the reaction when you aren't at equilibrium. So what we're going to do to figure out if a precipitate will form is we're going to start by writing the mass action expression for the dissolution reaction, which in order to do that, you will need to write a balanced chemical reaction. Second, we're going to calculate our ion concentrations after dilution. So when you did precipitation reactions in lab, what you noticed was that you had two solutions where everything was perfectly dissolved, and the precipitate did not form until you poured those two solutions together. So precipitation always happens after you combine two solutions, but the act of combining those two solutions also dilutes the solutions. So we have to use our normal dilution calculations to calculate actual ion concentrations after you combine the solutions. So once we have those concentrations, we're going to plug them into our mass action expression, and we're going to calculate our reaction quotient Q. And then we're going to compare the Q value that we calculated to our solubility product. If the Q value is larger than our KSP, then we know we are going to get a precipitate. If our Q value is less than or equal to our KSP, then we don't get a precipitate. So let's try that with a problem. This reaction is one that should look familiar to many of you, in that what we're doing is we're mixing sodium chloride with sodium nitrate. And so those of you who had a chloride or an iodide as your unknown ionic compound in lab know that we got a precipitate out of this. Now, one of the things you have to decide when you're combining two solutions of ionic compounds is what is your precipitate actually going to be? And the way we think about it is we look at the cation of one compound and the anion of the other, and then the anion of that other compound with the cation of the first one. So we can either have sodium nitrate or we can have silver chloride. So the old way you used to do this is to look at your list of soluble and insoluble compounds. The cool equilibrium way to do this is to look at the KSPs. So the smaller the KSP, the more likely it is to precipitate out of solution. So if you look at the KSPs that are given in the problem, you see that the KSP for AgCl is basically 10 to the minus 10th. The KSP for sodium nitrate is 1.03. So that's 10 orders of magnitude difference. It's very clear that AgCl will be our precipitate. So let's write a mass action expression for AgCl. Here is our balanced chemical reaction. And so our mass action expression is just going to be the silver concentration times the chloride concentration. Our second step is to calculate the ion concentrations after dilution. There are a few things we have to calculate in order to do this. The first thing is, after we put our solutions together, what will the combined volume be? Well, we have 100 mils of sodium chloride solution and we have 100 mils of our silver nitrate solution, so that's going to give us a total of 200 mils after we combine them. And I've converted that to liters because at some point we're going to have to divide by a number of liters. Next, we're going to calculate the number of moles of silver ion. So originally we had 100 mils of 0.10 molar solution, and so we're going to multiply those two, and you can see that the liters will cancel out. That will give us moles of solution, so we have 0.010 moles of silver. So what will the molarity of silver ions be after dilution? Well, let's take that number of moles, because the number of moles won't change. Let's divide it by our total volume after we combine them. and that gives us a molarity of 0.050 molar. So technically, we should also calculate the number of moles of chloride and the molarity of chloride after dilution, but we have the exact same molarity and the exact same combined volume for chloride that we did for silver, so they're going to have the same concentration. So now we're going to take our concentrations that we calculated in the previous step, and we're going to plug them into our mass action expression to calculate Q. So Q in this case will be the silver concentration times the chloride concentration. That's going to be 0.050 times 0.050. And that's going to give us a Q value of 2.5 times 10 to the minus 3. For our last step, we compare our Q value to our KSP. So Q is 2.5 times 10 to the minus 3rd. KSP is 1.8 times 10 to the minus 10th. Obviously, our Q value is much, much larger than our KSP, and that tells us we are going to get a precipitate. And this is not surprising, because when we put these solutions together in lab, and they did have approximately this concentration, we did get a precipitate forming. So that's our sort of self-check for this problem. Solubility is not straightforward again, and so learning to play with KSP and also the Q, the reaction quotient for a system, will help us understand whether things will dissolve and whether we will get a precipitate forming. I hope this was helpful, and I will see you again soon.